working on our last example here. In the last video, we had a crash course on Bayesian statistics. If you remember that crash course, we had this idea that Bayesians are interested in the posterior distribution. And what we mean by posterior distribution is it's a distribution of some parameter given the data. So Bayesians had this fundamental philosophy that parameters are not fixed values that really exist and are to be pinned down. They're just abstractions we use, and some values are more likely than others. Or in other words, the parameters themselves have a distribution describing which values are more or less likely for a given set of data. And using Bayes' rule, we saw that the posterior distribution was proportional to the likelihood, and that was our distribution of our likelihood of the data given a particular value of the parameter times our prior belief about what are likely values of the parameter theta. So we're going to use this Bayesian setting now and combine that with Metropolis-Hastings to figure out how to draw samples from a posterior distribution. So again, we'll use Metropolis-Hastings algorithm to generate samples that converge to this stationary distribution or this posterior distribution. Then we'll have an idea of the likely values of our parameter. So for this setting, let's use something familiar. X is going to be from a binomial distribution, and that means that our PMF of X, given a particular parameter, or in other words, the probability that we observe a particular value little x, given some parameter p, and sorry about this, there's probably a little typo in your notes, this didn't render correctly. This should be n choose x, number of ways we can choose x successes in our n fixed trials, times p to the x, so probability of success, I've got x of those, and then 1 minus p, it's my chance of failure. I've got the remaining n minus x failures. So in practice, we don't know p. That's typically unknown. Frequentists view that as a distinct value that's out there, that exists, and we might try and pin it down with a confidence interval or something like that. Bayesians do not view this as a fixed value. Instead, it's got a distribution, and we're going to be specifically interested in that posterior distribution. What are the likely values of p given some evidence or observed data? So to get our observed data, we're going to conduct the binomial experiment that has n trials with this unknown p, probability of success, and we're going to do that m different times. So I have m different values, observed data points, representing how many successes I observe when I conduct this binomial experiment. So x is going to represent my data, and again, I've got number of successes for binomial experiment with n trials. I'm going to do that one time and get x1. I'm going to run the binomial experiment with n trials. Again, get x2, number of successes. I'm going to repeat that m times. And so to figure out this idea about the distribution of likely values of p given the data, we need to first figure out our likelihood and our prior. So the likelihood, probability of observing the data for a given value of the parameter. Remember, the data is a vector now. I don't have just one observation, one number of successes. I've got m of them. And I should emphasize, it's not written up here, but these are generated independently. It's repeated m times, each of those m times independently. So I'm allowed to just multiply the probability of seeing the first one times the probability of seeing the second, and so on. So the PMF for a given probability of success for that number of successes, and I can just multiply those over my m trials because they're independent, or my m repeated experiments. So next line, I'm just plugging in. Here's my f of xi given p, the binomial PMF. I have that multiplied together m times for my different values of xi. And notice where we're headed is the distribution of p. So this first term doesn't have a p in it, so I'm going to just toss that out. That n choose x, there's no p or parameter, my variable now. The probability of success is my variable. That's not in this term. I can toss it out and say it's proportional to this part. Probability of p to the x, 1 minus p to the n minus x. But I've got this multiplied together for my m repeats of this experiment. So p to the x1, 1 minus p to the n minus x1. Same thing for x2, all the way to xm. I can just combine like terms here, so I have p to the x1 times p to the x2 times p to the xm. So that's p to the sum of all those x's. And similarly, 1 minus p. And then here, I've got n in each of these. I've added them up m times, so m times n minus the sum of the xi's. So this is my likelihood distribution. Next, we need the prior distribution to figure out what this posterior distribution is going to look like. So the prior distribution is our prior belief about p. So in this case, p is a probability. So it makes sense that p is coming from a distribution that lies in the space of 0 to 1. So that makes sense. We should use a beta distribution as our prior belief or prior distribution. Beta lives on 0, 1, which is appropriate for describing our parameter p, a probability. So as a reminder, here's the PDF for a beta distribution. Notice in here, I'm writing this as my variable is p. Normally we see x in here, but p is our variable. We don't think p is a fixed value. We think it has a distribution. So this is my prior belief about the distribution of p. And again, just plugging it in for beta generically. P is my variable. Keep saying that. You have to keep telling yourself that. So this part, my normalizing constant, I don't care about. It's going to be proportional to just this kernel that involves p. And again, p lives in 0 to 1. So a couple comments about this prior. Hopefully it makes sense why we're choosing beta, the whole lives in 0 to 1 thing. But we might want to pause and think about, well, what values of alpha and beta should we use to define this beta distribution? If we use alpha and beta as 1, that gives us a uniform 0, 1 distribution. This is called a flat prior or non-informative prior or uninformative prior. And that should make sense because we've got, here's between 0 and 1. Here's my prior belief, f of p. It just looks like this, telling me, oh, I'm equally likely to observe a probability of success anywhere in 0 to 1. I have no idea what's going on. It could be a very rare thing that happens, or it could happen all the time. So I could have anything in between. So this is non-informative. It could be equally likely to be any of these things. However, maybe you have a little bit of subject matter knowledge, and you think, well, this is kind of a rare event, so you might choose alpha and beta to give you something like this. So where p, this would tell me values of p are more likely to be small, indicating a rare event, rather than large. So you would choose alpha and beta that give you a shape like this, indicating low chance of success. Or vice versa, maybe you know this is a common event, your chance of success is pretty high. So maybe your beta distribution looks something like this. You want to choose alpha and beta that indicate p, large values of p, are more likely. So your choice of prior really depends on your subject matter knowledge. No idea what's going on, that's the first one, our flat prior. Or it's known to be a fairly rare event versus known to be a fairly common event. Now let's put all those together. Remember our golden rule of Bayesian statistics? I don't know that that's a real saying, but I like using that saying. The posterior is proportional to the likelihood times the prior. So let's start filling that in. Let's putting that together. So our likelihood we had earlier was proportional to p And actually, I'm going to use proportional again here because I'm not going to write down the likelihood. I'm going to write down what it's proportional to. So that was p to the sum of the xi's, 1 minus p to the nm minus sum of the xi's. Okay, so there's our likelihood from above. And then our prior, we just wrote down, was proportional to p to the alpha minus 1, 1 minus p to the beta minus 1. And if we start kind of combining like terms, we get something like this, p to the alpha plus sum of the xi's minus 1 times 1 minus p, combine those two terms together, and we get beta plus nm minus sum of the xi's minus 1. So if you look at this, you should be noticing something. Our posterior distribution has the same format yet again. This looks a whole lot like the beta distribution once again. So this is, let's say, i.e., the posterior is another beta distribution, but my alpha this time is alpha plus xi, or plus the sum of the xi's, and my beta is this term, so it's still in the form of p to the something minus 1 and 1 minus p to the something else minus 1. So this first something is my new alpha, alpha plus sum of the xi's. This new something this is my new beta, so beta plus nm minus sum of the xi's. Okay, so this is my posterior distribution, is also a beta distribution, and notice it, the parameters take into consideration alpha and beta from my prior belief, and then also the sum of the xi's from the data I've observed. I'm going to call this guy alpha star just to keep it simple, this guy beta star to keep it simple. So you might need to flip over depending on the size of your writing. If you just want to throw out a quick definition here. When we have something like this happen, when the prior, in our case that was beta, and the posterior, we noticed, hey, that was also a beta distribution. When those have the same distribution, we call them conjugate distribution. So this is fairly common in Bayesian statistics. You can look up all kinds of combinations of conjugate distributions. So just a few observations before we look at generating a Markov chain that converges to this distribution. Let's look at the mean of the posterior distribution. So posterior mean, we just saw the posterior distribution is beta. The mean of a beta is alpha over alpha plus beta. So we're going to plug in the alphas and the betas for that posterior distribution. I've redefined them up here just for reference. So alpha star is alpha plus sum of the xi's. And then our denominator is going to be our alpha star plus beta star, so plus nm plus beta minus sum of the xi's. We can simplify a little bit here, so we get alpha plus sum of the xi's over alpha plus nm plus beta. So just an observation, as we have more and more data, this sum of the xi's and this nm term are going to increase. So I'll say as data increases, so sum of xi and nm increase, then this ratio is going to be dominated by the data, this ratio of the sum of the xi's and nm. And our constants, alpha and beta, from our prior belief aren't going to play as much of a role. So as data increases, the role of the prior, and those were defined by our parameters alpha and beta, decreases. Okay, so if we don't have much data, our prior belief will play a big part in our posterior distribution, the alpha and the beta. If we do have a lot of data, our prior belief really won't play a huge role. So it's kind of this balancing act between your prior belief and the evidence you have. As you have more and more evidence, that will slowly start outweighing your prior belief, playing a more important role. Similarly, if you look on your little cheat sheet for the variance of the beta distribution, you'll get an expression like this. And if you plug everything in there, we get alpha plus the sum of the xi's times nm plus beta minus sum of the xi's in the numerator. And then our denominator, alpha plus beta plus nm plus 1 times alpha plus beta plus nm squared. I had skipped a few steps there, but it'll simplify to this. And then another observation here, as the available data increases, our variance should be decreasing. So if you look in the denominator, we've got this nm term, and it'll be kind of to the power of 3 here. We've got squared here, one of them here. So that's going to dominate, and as our data increases, the variance, or this term, is going to get smaller and smaller. So as data increases, variance decreases. So again, thinking about the role of data versus the prior belief, how that's going to affect the posterior distribution. So let's wrap this video up by checking out our pseudocode for actually implementing this algorithm. So a reminder, our goal is to to construct a Markov chain whose stationary distribution is this posterior distribution. So we have that posterior distribution, which was beta distribution, that contained prior belief and data in it. And our goal is to use the Metropolis-Hastings algorithm to come up with a chain that will converge to that posterior distribution. So our usual steps, we need to sample from the proposal. Our proposal, I'm going to suggest we use a uniform distribution for the proposal. So we need a proposal that contains the space of our variable. So here our variable is p, and p lives between 0 and 1, so uniform 0 and 1 will work. They contains a space of p, our posterior distribution. And it's also really easy to sample from, and it's symmetric, and it's independent of our current position. We had those specific cases for the Metropolis-Hastings algorithm. So that'll make our expression for rho a lot simpler. So we'll set t equal to 1 and initialize, and we've been using xt, I'm going to change it up, keep us on our toes, use pt to remind us p is our random variable, the probability of success. And I'm going to initialize that probability of success somewhere in 0, 1. Then we'll generate a value from our proposal, uniform 0, 1. So that means our q of y given pt is just 1. So this is symmetric. Q of pt given y is also 1. And it's also independent. This expression does not depend on pt, that given information. So symmetric and independent. So our next step is our acceptance rejection. Our p of t plus 1, our next state in the chain, is either going to be our proposed value with probability rho, or our current position pt with probability 1 minus rho. Rho is our usual expression. I kind of left this off here. This is our q of pt given y in the numerator, and our q of y given pt in the denominator. we mentioned those are both 1, so that just kind of cancels out here. So we just have that ratio of the probability of our proposed value versus our current position. And remember, F is our target distribution. So our target distribution was the posterior distribution, or the beta distribution with parameters alpha star and beta star. So evaluated at y, our current position, so y to our alpha star, 1 minus y, to the beta star minus 1. And then denominator is that distribution evaluated at our current position, pt. So pt to the alpha star minus 1, 1 minus pt to the beta star minus 1. Update our time step and keep repeating until our chain has converged. All right, we're going to end our notes here. In the last section, we'll check out how to implement this in R and get a feel for the results.